Imagine an ordinary morning in a high-tech laboratory. A sleepy graduate student watches a computer screen glowing with data from an experiment that was supposed to be routine. Then the numbers begin to drift in a way no one had predicted. Lines on a graph shiver like something alive. An alarm that has never sounded before suddenly shrieks. The student calls for their supervisor, and soon a group of scientists are staring at the display in disbelief. What they are seeing looks less like the smooth progression of a physical measurement and more like a glitch in a video game. Could the universe itself be betraying a secret? This is not the plot of a science fiction film. It is a description of how some researchers felt when they thought they had caught the cosmos doing something it was not supposed to do. The idea that reality might be an illusion, a simulation running on some unimaginably powerful computer, has captivated philosophers and physicists for generations. In the cultural imagination, this notion is often linked to the green code cascading down the screens in a famous film. But in recent decades, it has moved from pure fiction into the fringes of scientific debate. One of the most intriguing hints pointing in that direction came from a physicist who was not looking for a glitch in reality at all. Melvin Vopson, a researcher at the University of Portsmouth, spent years studying the thermodynamics of information, and he noticed something he could not easily explain. According to the second law of thermodynamics, the disorder, or entropy, of an isolated physical system cannot decrease. But when Vopson looked at the evolution of digital files and biological molecules, he found that their information entropy often remained constant or even decreased. To make sense of this, he proposed a new law that he called the second law of infodynamics. In his view, information behaves differently from heat or mass. It seems to organize itself over time, compressing data, optimizing storage, and reducing redundancy. In the everyday world of computers, this makes sense. Compression algorithms reduce file sizes by eliminating repetitive patterns. But Vopson claimed that this principle applies on every level, from the way electrons arrange themselves around atoms to the way genes mutate in viruses. During the pandemic, vast numbers of genetic sequences from the virus that causes COVID were made public as researchers tracked variants. Vopson treated these sequences like a stream of digital data. As the virus mutated, he calculated that its information entropy decreased. The mutations were not purely random. Instead, they seemed to nudge the genetic code toward a more ordered, efficient state. For him, this was evidence that the universe may contain a hidden algorithm. If information entropy is driven down across biological systems and digital media alike, perhaps there is a universal optimization at work. Vopson even suggested that information could have mass. He pointed to experiments in which erasing bits on a hard drive produces a tiny amount of heat, implying that information contributes to a system's energy. He proposed weighing a storage device before and after deleting data to detect a change in mass so small that current instruments cannot measure it. In a dramatic extension of his idea, he described an experiment in which particles and antiparticles would annihilate, not just producing light, but also erasing their intrinsic information. If his predictions about the frequencies of the resulting photons were confirmed, he argued, that would support the idea that information is a fifth state of matter, and that the cosmos is running a kind of compression program. Vopson was not content to let this remain a speculative curiosity. He took his argument to the wider public, evoking cinematic stories in which a hero wakes up from a digital dream. He suggested that the tendency of information to compress could be the fingerprint of a simulation. In a simulated universe, he reasoned, data optimization would be essential. Without built-in compression, the computational load would become prohibitive. He pointed out that digital data, biological systems, mathematical symmetries, and even cosmic structures all show signs of optimized information. If random mutations are guided toward a decrease in information entropy, and if symmetries in nature reflect the most efficient organization of data, then perhaps someone or something has programmed this universe to save memory. It was a bold claim. Supporters saw it as a tantalizing clue. Critics saw it as a stretch. News articles dutifully reported that these ideas require much more evidence, noting that there are as many papers refuting the simulation hypothesis as promoting it. To appreciate the audacity of Vopson's work, it helps to understand the thermodynamic principle he builds on. In the early 1960s, IBM physicist Rolf Landauer argued that erasing a single bit of information releases a minimum amount of heat. This insight, known as Landauer's principle, tethered computation to thermodynamics. In the decades since, experiments have verified it for systems as small as single electrons and as complex as superconducting circuits. Vopson extended the idea to mass. In his mass-energy information equivalence, A bit at room temperature has a mass of roughly 3.19 times 10 to the minus 38 kilograms. If you were to delete a terabyte of data, the mass of your storage device would decrease by about 2.5 times 10 to the minus 25 kilograms. That difference is smaller than the mass of a single proton, but the prediction is specific. According to his proposal, matter-antimatter annihilation should produce not only the usual gamma rays, but also a pair of additional low-energy photons in the infrared, with wavelengths of roughly 50 micrometers. Detecting such photons would lend support to the idea that information has mass and that erasing it produces measurable radiation. The experiment would be challenging because the extra photons are extremely faint, and many processes can produce infrared light. But the boldness of predicting new particles from information erasure captured imaginations. Perhaps information truly is a fifth state of matter alongside solids, liquids, gases, and plasmas. If so, its behavior might offer a window into the machinery of the cosmos. The importance of information is not abstract. By Vopson's reckoning, typical atoms carry bits describing their mass, charge, and spin. When this single particle information is multiplied by the number of particles in the universe, it yields an estimate of about 6.036 times 10 to the power of 80 bits. That number is staggering, yet it pales in comparison to the deluge of data created by humans each day. On an average day, the world produces hundreds of millions of messages, emails, and social posts, billions of messages and tens of billions of communications across various platforms. In the year 2020, the total amount of digital information created, captured, and consumed globally was roughly 59 zettabytes. Forecasts by a major market intelligence company predicted that by 2025 that number would almost triple to roughly 175 zettabytes. A single zettabyte is 8 billion trillion bits. If current trends continue, researchers warn that in just a few centuries the number of digital bits we create could exceed the number of atoms on Earth. Within a little over a century, the energy required to sustain this information production may exceed the total power consumption of the entire planet. Vopson refers to this looming scenario as the information catastrophe. From this perspective, the drive to compress and optimize data is not a quirk of a hypothetical simulation, but a necessity for our own survival. If information does have mass, then storing too much of it could quite literally weigh down our technological infrastructure. Whether or not the universe is simulated, the physicality of information imposes limits that society will have to grapple with. While some researchers look at genetic codes and see data compression, others look up at the heavens. High-energy cosmic rays, which are charged particles traveling through space at energies millions of times greater than those produced by earthly accelerators, occasionally slam into detectors on Earth. These particles, mostly protons, originate from energetic astrophysical events such as supernovae and the jets of active galaxies. In the early 2010s, a team led by Silas Bean, Zohre Davoudi, and Martin Savage at the University of Washington asked a strange question. What if the space-time we inhabit were not continuous but a lattice, like the grid in a digital game? If future beings wanted to simulate a universe from the ground up, they might discretize space and time into tiny cubes. That lattice spacing would create an inherent maximum energy. Anything beyond it would be cut off because a simulation cannot represent features smaller than its pixels. Bean and his colleagues realized that ultra-high-energy cosmic rays might offer a way to probe this. When cosmic rays travel through the cosmos, they collide with photons of the cosmic microwave background, the relic radiation from the Big Bang. These interactions produce a theoretical limit on cosmic ray energies known as the GZK cutoff. Bean's team calculated that if a simulation's lattice spacing were of a particular scale, then the pattern of arrival directions of the highest energy cosmic rays would exhibit a faint imprint of the underlying grid. Instead of coming evenly from all directions, the most energetic events would cluster along axes aligned with the lattice. They estimated that the inverse lattice spacing would need to be greater than roughly 10, raised to the power of 11 giga-electron-volts. So far, observations show a decline in cosmic ray flux around the predicted cutoff, consistent with interactions with the microwave background. No clear cubic pattern has emerged, but the mere possibility that cosmic rays could reveal a digital grid sparked the imagination of both physicists and the public. On the largest scales, another class of anomalies has ignited speculation. The cosmic microwave background is a faint glow that fills the universe, the afterglow of the hot early cosmos. Satellite missions such as WMAP and Planck have mapped its tiny temperature fluctuations with exquisite precision. In the mid-2000s, researchers noticed that the quadrupole and octupole components of these fluctuations, patterns describing how the hot and cold spots are arranged, seem to line up with one another and with the plane of our solar system. They dubbed this unexpected alignment the axis of evil, a tongue-in-cheek phrase hinting that it could undermine our assumption that the universe is isotropic. If the cosmos has a preferred direction, that could in principle be evidence of a larger structure or even an artifact of simulation. Over the years, some studies have suggested that the axis of evil may be a statistical fluke or the result of systematic errors in data processing. Others have argued that the alignment persists even in improved data. The debate remains unresolved. Importantly, some analyses comparing isotropic and anisotropic cosmological models have found no evidence for a fundamental anisotropy. Even if the alignment were real, it would be a far cry from proving we live in a simulation. Yet the phrase axis of evil continues to crop up in discussions about cosmic glitches. If cosmic rays and microwave maps are the grand canvases of the universe, the double-slit experiment is one of physics' smallest theatrical stages. First performed in the early 19th century, it demonstrates that light can behave like both a wave and a particle. In its modern quantum formulation, the experiment is simple and mind-bending. When light or electrons pass through two slits, they create an interference pattern on a screen, a series of bright and dark fringes. If you try to watch which slit a particle goes through, the interference disappears, and the pattern becomes two bright bands, as if the particles suddenly decided to behave like pellets. The more precisely you know the path, the less wave-like the outcome becomes. In recent years, researchers have stripped the experiment to its essentials. They have used individual atoms in a vacuum chamber to act as the slits, and sent in weak beams of light so that each atom scatters at most one photon. By preparing the atoms in different quantum states, they control how much information is gained about the photon's paths. They confirm with atomic-level precision that the dual nature of light is real, that you cannot simultaneously observe its particle and wave characteristics, and that knowledge itself changes outcomes. Stranger still, these modern experiments follow a suggestion Albert Einstein made almost a century earlier. He imagined hanging thin slits by springs and measuring the recoil when a photon passed. Today's experiments use laser light to hold atoms in place and effectively change the springiness to tune the fuzziness of each atom. Even with such ingenious variations, the conclusion remains the same. When you measure which path a photon takes, the interference fades. To those hoping to find a glitch in reality, the double-slit experiment may feel like one, but physicists see it not as a malfunction, but as a fundamental feature of quantum mechanics. It tells us that the universe at its most basic level does not follow classical rules. It is probabilistic and relational, and observation is part of the process. Variations such as the quantum eraser push the weirdness even further. In these experiments, particles are entangled with markers that record which path they take. In a delayed choice quantum eraser, the decision to erase or preserve path information is made after the particles have already passed through the slits. Remarkably, when the which path information is erased, the interference pattern reappears even though the choice is made after the event. This has prompted headlines about retrocausality, suggesting that the future affects the past. In reality, nothing travels backward in time. The key is entanglement. The patterns emerge only when the relevant subsets of the data are sorted by the outcome of the path markers. Quantum mechanics forbids us from ascribing a definite trajectory and interference pattern at the same time. The erasure does not change what happened. It changes the correlations we examine. While that subtlety is often lost in popular accounts, it highlights a recurring theme. Knowledge and reality are intertwined at the quantum level. That interplay feels like magic, but it is well described by the mathematics of quantum theory. There is no need to invoke simulation. The universe itself is stranger than any human-made code. The simulation hypothesis did not originate from cosmic anomalies or quantum experiments. It emerged from philosophy and probability. In the early 2000s, the philosopher Nick Bostrom proposed a trilemma that has haunted late-night conversations ever since. He argued that one of three statements must be true. First, almost every civilization that reaches the technological capability to run high-fidelity simulations of conscious beings will destroy itself, or fail to reach that stage. Second, such civilizations may reach a post-human stage but will choose not to run ancestor simulations, perhaps because they have ethical reservations or lack interest. Third, if neither of the first two statements is true, then the fraction of all people who live in simulations will be overwhelmingly large, and we almost certainly are among them. The argument is simple anthropic reasoning. If post-human beings create countless simulated universes populated by conscious minds, the number of simulated minds will vastly outnumber the number of unsimulated ones. Therefore, by probability alone, any randomly chosen mind is almost certainly simulated. Bostrom emphasized that he was not claiming we live in a simulation. He was highlighting a logical disjunction. Some people read the argument and become convinced that extinction or self-restraint by future societies is more plausible than the idea that we are simulated. Others embrace the third option as almost obviously true. Philosophers and physicists have debated the assumptions behind the trilemma: whether simulations would be conscious, whether advanced civilizations would have the resources and desire to run them, and whether the number of simulations would indeed be enormous. While the simulation argument stirred imaginations, some scientists decided to attack the idea head-on. In the autumn of 2025, researchers at the University of British Columbia's Okanagan campus published a study that they claimed mathematically proves that our universe cannot be a simulation. Mir Faisal and his colleagues drew on Gödel's incompleteness theorem, a result from mathematical logic that shows that within any sufficiently powerful system, there are true statements that cannot be proven within that system. They argued that a complete and consistent description of physical reality requires something beyond algorithmic computation. The foundations of physics, they said, rest on non-algorithmic understanding, concepts that cannot be captured by a sequence of computational steps. A simulation, by definition, is algorithmic. It follows explicit instructions. If the fundamental laws that give rise to space and time themselves are non-algorithmic, then no computer could emulate them. The team also emphasized that the fundamental laws cannot be contained within space and time, because they generate space and time. A simulation would have to embed these laws within its computational framework, but those laws would not fit within any finite algorithm. Their conclusion was stark. Because reality's deepest layer is non-algorithmic, no computer simulation can reproduce it. In other words, the universe cannot be, and could never have been, a simulation. Other researchers approached the question from a more practical, energetic perspective. In the mid-2000s, astrophysicist Franco Vatsa and his collaborators published a study in which they assessed how much information and energy would be required to simulate the universe. They examined 3 scenarios: simulating the entire visible cosmos, simulating the Earth at full resolution, and simulating the Earth at a coarse resolution that still respects observations of high-energy neutrinos. In each case, they found that the computational resources needed are beyond astronomical. The amount of energy required to encode all the information in the visible universe on a holographic boundary is so vast that even a civilization harnessing the power of galaxies would be unable to supply it. Even low-resolution simulations of the Earth would demand energy outputs comparable to the most energetic processes known, such as galaxy cluster mergers or distant quasars. Their work builds on the holographic principle and the Bekenstein bound, which link information content to physical area and energy. The underlying message is clear. Physics places hard limits on computation. If information truly is physical, then simulating a world like ours requires physically impossible amounts of resources. Proponents of the simulation hypothesis counter that a simulator would not need to compute everything down to the Planck scale. Bostrom himself acknowledges that simulating the entire universe down to quantum level is infeasible and likely unnecessary. Philosophical supporters suggest that only the subjective experiences of simulated beings need to be rendered without anomalies. Vast swathes of unobserved reality could remain low resolution or simply uncomputed until required. This back and forth illustrates that even when physics sets hard limits, philosophers can redraw the boundaries of what a simulation might entail. Long before anyone dreamt of binary bits or silicon chips, humans wrestled with the idea that the world might be a shadow of something deeper. In the allegory of the cave, Plato imagined prisoners watching flickering images projected on a wall and mistaking those images for reality. In Eastern philosophies, the concept of Maya describes the universe as a veil, an ever-changing appearance that hides an unchanging truth. Many indigenous traditions speak of dreams and visions as windows into more fundamental realms. These ancient metaphors differ from modern simulation talk in important ways. They emphasize moral and spiritual transformation rather than computational architecture. They invite listeners to turn inward, to recognize the limits of perception and the possibility of awakening. When philosophers today invoke simulations, they often focus on the agency of a programmer and the physics of the code. Yet the underlying intuition is similar. What we perceive may not be all that exists. Recognizing these parallels can enrich the current debate. The ancients did not become nihilists because they saw the world as an illusion. Rather, they found meaning in navigating the illusion with kindness, courage, and curiosity. Similarly, thinking of the universe as a simulation need not lead to despair. It can be a prod to humility, a reminder that our knowledge is partial. It can inspire us to look more carefully, to test our beliefs, and to appreciate the wonder of existence, whether or not it rests on a substrate of code. When people point to patterns such as the golden ratio in the spirals of galaxies, or the fractal branching of rivers and neurons, they are not necessarily finding proof of design. They are expressing awe at the self-organizing power of nature. The cosmos is full of emergent regularities that, to a mind steeped in software, resemble algorithms. But that resemblance could be just as meaningful as it is metaphorical. Science advances by creating models and metaphors. It also matures by knowing when to let them go. The simulation hypothesis also faces more mundane criticisms. Sabine Hossenfelder, a theoretical physicist known for her clarity and candor, has called the idea pseudoscience. She notes that there is no way to test whether we are in a simulation without making extra assumptions about the simulator's motives and capabilities. Cosmologist George Ellis has described the hypothesis as late-night pub conversation. The anthropic reasoning in the simulation argument also assumes that simulated beings have conscious experiences indistinguishable from those of non-simulated beings. That assumption is far from obviously true. Philosophers have argued that a simulation could produce the behavior of consciousness without the experience, and that such minds might not count as conscious in the morally relevant sense. Others have suggested that if simulations exist, they might be limited to particular brain regions, hallucinations, or training exercises rather than entire universes. Just when it seemed the conversation might settle, a new series of discoveries sent the narrative plunging and climbing again. Researchers began to look for more concrete glitches in the forces that govern the cosmos. In the spring of 2024, a team led by Robin Wen and Nyayesh Afshordi proposed a subtle modification to Einstein's theory of general relativity. Their model suggests that gravity behaves exactly as Einstein predicted on small scales, but becomes about 1% weaker over distances spanning billions of light years. The researchers describe this weakening as a cosmic glitch, a small correction that smooths over inconsistencies in cosmological data without undermining the many triumphs of general relativity. For nearly a century, astronomers have observed that distant galaxies appear to recede from us faster than those nearby, and that the rate of expansion seems to accelerate. The standard explanation invokes dark energy, a mysterious component with repulsive gravity. Wen and his collaborators proposed that instead of a new energy component, gravity itself might transition between a cosmological regime and a Newtonian regime at cosmic scales. In their analogy, Einstein's equations still hold, but once you reach the cosmic equivalent of fine print, terms and conditions apply. If their model is borne out by observations, it will not prove that we are in a simulation, but it will underscore that even the most established theories can be revised in the face of new evidence. Like the axis of evil, this cosmic glitch may turn out to be a systematic error or a fluke, or it may signal new physics that redefines our understanding of space, time, and gravity. The notion of glitches is not confined to abstract cosmology. Our own planet has exhibited anomalies that at first seemed inexplicable. Between the years 2006 and 2008, twin satellites of the Gravity Recovery and Climate Experiment, known as GRACE, detected unusual fluctuations in Earth's gravitational field. The anomaly stretched roughly 4,350 miles across the eastern Atlantic and consisted of a region of unusually strong gravity adjacent to a region of unusually weak gravity. At first, scientists thought the ocean might be responsible, but the mass distribution could not be explained by water alone. A team led by Charlotte Gage-Gurentin traced the signal deep beneath the crust near the base of the mantle. They proposed that minerals in the lower mantle undergo a phase transition under extreme pressure and heat. The mineral bridgmanite transforms into a less dense phase called post-perovskite. Such a transformation would redistribute mass at the core mantle boundary and alter the local gravitational field. In other words, Earth's gravity glitched because crystals deep inside the planet changed shape. The anomaly lasted only a couple of years, but it reminds us that what appears to be a flaw in reality may instead be a window into hidden processes. The same satellites that can detect melting glaciers and draining aquifers can also reveal the dynamic, changing mineralogy of the deep Earth. Such insights underscore that not every glitch points to simulation. Sometimes it points to geology. Many of the quantum experiments that inspire talk of glitches involve more than just two slits. Consider again the quantum eraser. Here, particles are entangled with markers that record which path they take. In a delayed choice quantum eraser, the decision to erase or preserve path information is made after the particles have already passed through the slits. Remarkably, when the which path information is erased, the interference pattern reappears even though the choice is made after the event. This has prompted headlines about the future affecting the past. In reality, no information travels backward in time. The key is entanglement. The patterns emerge only when the relevant subsets of the data are sorted by the outcome of the path markers. Quantum mechanics forbids us from ascribing a definite trajectory and interference pattern at the same time. The erasure does not change what happened. It changes the correlations we examine. While that subtlety is often lost in popular accounts, it highlights a recurring theme. Knowledge and reality are intertwined at the quantum level. That interplay feels like magic, but it is well described by the mathematics of quantum theory. There is no need to invoke simulation. The universe itself is stranger than any human-made code. The universe also poses puzzles that are measured in megaparsecs rather than microns. A current example is the so-called Hubble tension. Astronomers use multiple techniques to measure the rate at which the universe expands. Observations of supernovae and variable stars in the local universe suggest a faster expansion rate than the one inferred from the cosmic microwave background and from the distribution of matter shortly after the Big Bang. The discrepancy is significant and has persisted even as measurements have improved. Some physicists speculate that unknown particles, early dark energy, or modifications to gravity might resolve the tension. Others suspect unrecognized systematic errors. A few enthusiasts call it a glitch in the cosmic program. Yet the more likely outcome is that resolving the tension will teach us something new about cosmic ingredients or measurement techniques. The pattern is familiar. A mismatch becomes an opportunity for discovery. Whether the solution is mundane or revolutionary, it will deepen our understanding of the cosmos without implying that someone typed the wrong value into a simulation. A different line of reasoning in the simulation debate involves physical limits on information storage. According to the Bekenstein bound and its cousin the holographic principle, the maximum amount of information that can be contained within a region of space is proportional not to its volume, but to its surface area. A black hole's entropy, for instance, scales with the area of its event horizon. Applied to the observable universe, this principle suggests an upper limit on the total number of bits that can be encoded in cosmic structures. While estimates vary, they hover around a number with more than 120 digits, an unfathomable but finite amount. Franco Vatsa's calculations draw on these ideas to argue that simulating the universe at fundamental resolution would exceed any plausible computational capacity. Proponents of the simulation hypothesis counter that a simulator would not need to compute everything down to the smallest scales. Bostrom himself acknowledges that simulating the entire universe down to the quantum level is infeasible and likely unnecessary. In commentary published in the mid-2020s, Elliot Edge and James Brown argued that astrophysical critiques often misinterpret the premise of the simulation argument by assuming that a simulator must render every microscopic detail continuously. Bostrom explicitly suggests that only the subjective experiences of simulated beings must be rendered without anomalies. Vast swathes of unobserved reality could remain low resolution or simply uncomputed until required. This back and forth illustrates that even when physics sets hard limits, philosophers can redraw the boundaries of what a simulation might entail. Amid the flurry of technical arguments, it is easy to overlook the psychological dimension of glitch hunting. Human minds are wired to find patterns. When we see a string of repeated numbers or a coincidence of birthdays, we feel as though the universe is sending a message. This cognitive bias, apophenia, helps us recognize faces in clouds and constellations in random star fields. It also feeds conspiracy theories and simulation speculations. Confirmation bias encourages us to collect examples that support a favored belief and ignore those that do not. The enormous amount of information we encounter each day increases the likelihood of apparent anomalies. In a world with billions of people, unlikely events become common. When a photographer captures a bird frozen in mid-flight with its wings aligned perfectly with a power line, it may look like a rendering glitch, but it is simply a moment of serendipity. Recognizing these cognitive tendencies does not mean dismissing anomalies out of hand, but it reminds us to apply statistical thinking before assuming supernatural causes. Still, there is something irresistible about imagining that our reality is written in code. Science fiction thrives on such speculation not because it is plausible, but because it provides a powerful metaphor for agency and control. In a world where algorithms curate our feeds and artificial intelligence writes our poems, the line between computation and reality feels thinner than ever. Even seasoned scientists admit to moments of doubt when confronted with inexplicable phenomena. The cosmic glitch narrative taps into a deep human desire to be part of a grand story. Whether that story is true is less important than how it motivates inquiry. If thinking about simulations leads us to examine the nature of consciousness, the limits of computation, the structure of the universe, and the ethics of creation, then it serves a purpose. What does all this mean for those who want to believe that they have glimpsed behind the curtain? The strong hook at the beginning of this story, that scientists found a glitch, stands on a knife edge between possibility and wishful thinking. Melvin Vopson's work on information entropy invites serious inquiry into the physical nature of information. His claims about data compression and genetic mutations are bold and require rigorous testing. They could lead to new insights into evolution and bioinformatics without supporting simulation. The cosmic lattice idea reminds us that our theories can be probed by looking for subtle signatures in high-energy astrophysics. The axis of evil encourages better data analysis and deeper understanding of the early universe. The double-slit and quantum eraser experiments continue to teach students that reality is more mysterious than classical mechanics. Bostrom's trilemma forces us to think about the future of civilization and the ethics of creating conscious beings. The mathematical proof that the universe cannot be simulated invites reflection on the foundations of physics. The astrophysical energy calculations show us the immense physical costs of computation. Together, these threads weave a rich tapestry of inquiry. Perhaps the most profound lesson is that whether or not we live in a simulation, we are part of a universe that produces beings capable of asking such questions. We have built machines that can weigh information and detect neutrinos. We have mapped the afterglow of creation and discovered the dance between waves and particles. We have used logic to explore possible universes and energy budgets. We have looked at viruses and seen patterns that may hint at new laws. We have told stories about waking up and choosing different colored pills. These achievements are real, regardless of the metaphors we use to describe them. The search for glitches in the fabric of reality is, in a sense, the search for our own limits. When we push against those limits, we expand the horizon of human knowledge. Even if we never find a programmer's signature hidden in the cosmic microwave background or a message embedded in prime numbers, we will have learned something about the universe and ourselves. The roller coaster ride of ideas, from shocking anomalies to sober refutations, keeps us engaged. It reminds us that science thrives on curiosity, and that sometimes the most interesting stories begin with the words, "What if?"